x of s is equal to Fourier transform of xt e to the power minus sigma t. Okay, where s is a complex variable, it is sigma plus j omega. Now we have seen that the Fourier transform of a signal exists only for which type of signals? The signal is?
Absolutely
The
integrable.
signal must be absolutely integrable. Now tell me, what is the condition for existence of Laplace transform? If you consider the Laplace transform x of s, for some value of s is a complex variable, for some value of s, if the Laplace transform exists, then what should be the condition? Can we say that the Laplace transform exists at some values of s only if this must be what?
Absolutely
This
integrable.
must be
Finite.
absolutely integrable. E to the sigma t into e to the power minus sigma t dt, this must be absolutely integrable. Normally we write this because e to the power minus sigma t is always greater than 0. xt e to the power minus sigma t dt, this must be absolutely integrable. Then the Laplace transform of the signal exists. Okay, otherwise it is not that for any signal xt Laplace transform exists. It is if for a signal that satisfies this condition. Okay, and here there is a difference as compared to the Laplace transform. Here we consider s of sigma plus j omega. Okay, and if this condition is satisfied, xt into e to the power minus sigma t dt, we can find the Laplace transform. If we plot this, s is a complex variable. I'm plotting it as real part of s and imaginary part of s. And normally it is written as sigma. This is called the sigma axis and this is called the j omega axis. Okay, this is the imaginary part and this is the real part of s. So it is a because it is a complex variable. S is a complex variable. Okay. Now, if you consider any signal xt and consider a point s here, what is the condition for existence of Laplace transform at this for this particular value of s? What is the condition for the existence of Laplace transform at this for this value of s? I am taking a particular value of s. What is the condition for existence of Laplace transform?
xt into e raised to power minus real
This is the
part of s.
condition. And what is the sigma here for corresponding to this? It is the real part. So if you consider this sigma, then next mod xt into e to the power minus sigma t dt must be absolutely integrable. And later on we see that for a signal and most of the signals, the Laplace transform exists only in some region of this plane. And let me this plane where the real axis this is the real part of s and imaginary part of s. This is called the s plane. This is called the s plane. And if you consider any point in this s plane, the Laplace transform exists only if this condition is satisfied. And those regions are called, it is called the region of convergence or the ROC. Okay. If you consider a signal xt, the corresponding ROC or region of convergence is the values of s for which the Laplace transform exists. Okay. xt is e to the power t ut. xt is e to the power t ut. Is this the shape of the signal? E to the power ut?
Yes, sir.
It is an exponentially growing signal, e to the power t ut. Does it have a Fourier transform?
No, sir.
No, because this is not absolutely integrable signal. Now, what is the Laplace transform of the signal? I can write the definition here. X of s is integral minus infinity to infinity xt e to the power minus st dt. Okay, and if you put it here, it is minus infinity to, because of this ut, this now this limit is from 0 to infinity, and e to the power t e to the power minus st dt, isn't it? And this is integral 0 to infinity e to the power minus s minus 1 t dt. Is it? What is that integral? What is that integral?
1 by s minus 1.
It is 1 by s minus 1. Is it? Is it valid for all the values of s?
Yes, greater than 1.
Sorry?
Yes, greater than 1.
Yes, greater than 1.
Real of s greater than 1.
Real of s greater than 1. Why? Because the condition for this is, we have seen that this Laplace transform, it is the Fourier transform of what? Fourier transform of xt into e to the power minus sigma t. Okay. So the condition for existence of this Laplace transform is, we can directly get from this, if this is absolutely integrable, then only this converges, this integral converges. So that condition for convergence is integral 0 to infinity e to the power t, because this 0 is coming from this ut, e to the power ut t into e to the power minus sigma t dt. Is it that? If this is finite, I am not taking the mode because both are positive for t greater than, for any value of t. Okay. Now, what is the condition? What is the condition? Integral 0 to infinity e to the power minus sigma minus 1 t dt less, it is finite. Is it that?
Yes, sir.
Now, when will this be converging? This one. For this to converge, this should be an exponentially decaying signal. And what is the condition? Sigma minus 1 should be what?
Greater than 0.
It should be greater than 0. So this will converge only for values sigma greater than 1. Is it? That is, this expression is valid only for sigma greater than 1. You cannot put this expression for any value of s. This expression is valid only when, generally we write this as when real part of s is greater than 1. Is it? And this is called the ROC, because in this region of s only this integral converges. This expression is valid. Otherwise, this is not a valid expression. And if you plot this in the s plane, this is sigma and j omega. What is that plane? What is the corresponding region in this s plane? What is the corresponding region? Is it this?
Yes, sir.
Sigma greater than 1. That means, draw a line here. If you consider any point in this region, that will have real part of s greater than 1. If you consider any point in this region, that point will have real part of s greater than 1. and this is a valid expression in this region. Okay, so this is the ROC in this particular case. Okay, now let us generalize this. This is called the ROC, region of convergence. Now I hope you understood what is meant by region of convergence. This expression is valid only in this region. That means the Laplace transform exists only for these values of S in this particular case. Okay, this is called the region of convergence, isn't it? So now let us see what is happening here. If you look at this, this is the signal xt e to the power t ut, and can we have the Fourier transform of this signal? Does it have a Fourier transform? The signal xt?
No, sir.
No, because it is not absolutely integrable. So what we are doing is Laplace transform of this signal is the Fourier transform of xt into e to the power minus sigma t, isn't it? We are multiplying this with some e to the power minus sigma t. And what will be the resulting signal? Will it be a growing exponential or decaying exponential? Or it depends on the value of sigma.
Decaying.
This is et, decaying. For which values of sigma?
Greater than 1.
If sigma greater than 1, the resulting exponential, this is an exponentially growing exponential, and this is a decaying exponential. And when sigma is greater than 1, you can easily verify that the resulting signal, the product of these two, that will be a decaying exponential. And that has a Fourier transform representation, isn't it? It has a Fourier series representation. If it is absolute, the resulting signal is absolutely integrable. So what we are doing here is in the Laplace transform, those signals which don't have Fourier transform representation, we multiply with a decaying exponential, and decaying exponential or growing exponential, that depends on the signal. Sometimes we'll have to multiply with a growing exponential. For example, if the signal is something like this in the negative side, then we will have to multiply with a growing exponential. We'll see some examples later. Okay, so basically what we are doing is we are multiplying with an exponential and making it an absolutely integrable signal. Okay, and if you remember the Fourier representation, all the Fourier representation, we are expressing a signal in terms of what? In terms of what? In terms of complex exponential e to the power j omega t. Is it that? That is the Fourier representation, isn't it? We are expressing, in the case of Fourier series, it is a linear combination, summation, and in the case of Laplace, in the Fourier transform, it is an integral. Okay, so basically we are expressing a signal in terms of e to the power j omega t. It means this complex exponentials. Now, can you tell me what are we doing here in the case of Laplace transform? We are writing in terms of e to the power st, isn't it? What is e to the power st? It is e to the power j sigma. Can we write it as e to the power sigma t into e to the power j omega t? Sorry, e to the power sigma into e to the power j omega t? Because s is sigma plus j omega, isn't it? Is it? So when we say that we express a signal in terms of complex exponentials, what is the real and imaginary part of this? Real part is a cosine signal, and the imaginary part is a sine wave, isn't it? Of e to the power j omega t, and this amplitude is 1. Is it? E to the power j omega t. Now what about this? E to the power, wait, it should be sigma t, isn't it? Because e to the power st, so it is sigma t. So what will be the shape of this? Real part of this and imaginary part of this e to the power sigma t into e to the power j omega t. if sigma greater than what? Sigma greater than 0, then will it be a growing exponential or decaying exponential?
Growing.
So it will be something like this, isn't it? E to the power. Okay, if you are considering e to the power st, then it is growing exponential. So real part of that is like this. And sigma less than 0, it is a decaying exponential. Okay. Is it? So here we are expressing a signal in Fourier representation. We are expressing a signal in terms of pure sinusoidal signals, and here it is in terms of decaying or growing exponentials multiply. Its amplitude is changing, isn't it, with respect to this sigma? So that is what we are doing in Laplace transform. If the signal is not absolutely integrable, we multiply it with e to the power minus sigma t to make it absolutely integrable, so that the Fourier transform of this resulting signal exists. Okay. Any question regarding this? Is it clear? Okay, so now let us consider few examples. You can easily find this e to the minus infinity to infinity e to the power minus at into e to the power minus st dt, isn't it? That is Laplace transform of e to the power minus at ut. So this will be 0, and this integral you will get 1 upon s plus a. Okay, so Laplace transform of e to the power minus at ut is 1 upon s plus a. Can you tell me what is the region of convergence here? What is the region of convergence? What is the condition?
Sigma greater than minus a.
Integral minus infinity to integral 0 to infinity e to the power minus at into e to the power minus sigma t. This must be absolutely integrable. Since both are positive, we can write like this. We don't need to take the mode here. E to the power minus at into, when will this happen? This is 0 to infinity e to the power minus it is a plus sigma, isn't it, into t dt. Okay, and this is from 0 to infinity because it is non-zero for, because of the ut term, it is non-zero only for for positive values of t. Now this is this integral is finite when this is a decaying exponential, isn't it? When will that happen? A plus sigma greater than what? This is e to the power minus a plus sigma into t. When will this be a decaying exponential? This exponential,
Positive.
when it is greater than 0. So the condition is that a greater than sigma greater than minus a. That is the condition. So the ROC is, we can write, this is sigma is generally written as real part of s greater than minus a. Okay, so this is the ROC, and this is a standard result. This will be provided in the this formula is you can check in that formula sheet that I provided. This is given. Okay, and another standard result is minus e to the power minus at. Here it is u minus t, flipped version. Okay, so is it a decaying? What is the shape of this signal? This exponential. Forget about the minus term now for the time being. What about the shape of this? E to the power minus at u minus t. What? Is it something like this?
Yes, sir.
Isn't it? It is. like this. Okay, now let us try to find the Fourier transform, Laplace transform of this. So that is integral minus infinity to 0 because of u minus t. U minus t is non-zero from 0 minus infinity to 0. Then there is a minus sign here, e to the power minus at into e to the power minus st dt. Okay, and that is integral minus infinity to 0 e to the power minus s plus a to t dt. So what is the Laplace transform? What is this integral?
1 by s plus a.
It is 1 by s plus a. So is it same as this? Both these signals are having the same Laplace transform, isn't it? The algebraic expression is same 1 upon s plus a, x of s. But what is the difference? What is the ROC here? What is the ROC? What is the ROC? If you take the mode of this, that should be absolutely integrable.
Plus a greater than
Sorry?
s plus a greater than 0.
S plus a greater than 0. So what is that condition? Real part of s less than minus a? Is it that?
Yes, sir.
Sorry?
Yes, sir.
This is the ROC. So you can see that, okay, let me write it here. So first result is e to the power minus at ut. Its Laplace transform is 1 upon s plus a, and the ROC is real part of s greater than minus a. And the second signal minus e to the power minus at u minus t. That is also 1 upon s plus a, but the ROC is different. So here the algebraic expression is the same Laplace transform for both the signals, but the ROC is different. So it is very important to specify the ROC. Without specifying the ROC, that Laplace transform is not complete. Okay, so whenever some question related to Laplace transform is asked in the exam, you have to specify the ROC also. Just let's say xt is equal to 3 e to the power minus 2t ut minus 2 e to the power minus t ut. This is a worked out example from Oppenheim. Can you tell me what is the Laplace transform of this signal? What is the Laplace transform of this part? You can use the standard result. What is the Laplace
3
transform?
by s plus 2.
It is 3 by s plus 2 minus, what about this? 2 by s plus
S
1.
plus 1.
S plus 1. Now what is the ROC of this? You can see, you can compare these two. Is it real part of what? Real part
S
greater than minus 2, and this is real part of s greater than minus 1 for this one. ROC means this expression is valid only for these values of s. Now tell me what is the ROC of x of s? This expression is
greater than minus 1.
it is real part of s greater than minus 1. It is the intersection of these two ROCs. Okay, so this is the ROC. And how can we plot this in the s plane? This is the s plane. So this is the point minus 1, minus 2. Is this the ROC? If you consider any point here to the right of this vertical line passing through minus 1, it is always in the ROC, isn't it? Is it?
Yes, sir.
That is the ROC. Okay. So here we can simplify this. This can be written as s minus 1 by s plus 2 into s plus 1. Okay. And we'll see that in many of the for many of the signals that we consider in this course, the Laplace transform of the signal is always in this form. This is a rational function in S. Rational function because it is a ratio of two polynomials, isn't it? In S. So the general form of a rational Laplace transform is x of s can be written as numerator polynomial divided by denominator polynomial. And many times it is convenient to represent this in a product form, that is x of s is, let's say, sorry, in this polynomial form bm minus 1 that is the numerator polynomial, and the denominator polynomial is, sorry, let's say n s n. Okay, ratio of two polynomials in S, and we can represent this in the product form, that is a constant times S minus, let's say, let me denote it as Z1 S minus Z2 up to we can write like this. Now what are these Z1 Z2 Zm? They are the what? They are the roots of this numerator polynomial, isn't it? Is it? Z1,
Yes, sir.
Z2, there are, because this is an mth order polynomial, there are m roots. So these are the roots of that numerator polynomial, and P1, P2 up to Pn, they are the roots of the denominator polynomial. Okay? And what is the value of x, zi, where I is from 1 to m?
0.
It is 0. That is why I have used this z1, z2, zm, this roots of the numerator polynomial. These are called the zeros of xs. Okay, zeros of x of s. And what about x pi? When s is equal to p1, p2, any of these values, that is
Not defined.
infinite, isn't it? Is it? That's why p1, p2, this p1, p2, pn, they are called the poles of xs. Okay, so for example, in this case, this example, it is x of s is s minus 1 by s plus 2 into s plus 1. So how many zeros are there in this case? There is only one zero at that is at 1, and there are two poles, isn't it? One at -2 and the other one at minus 1. And in the s plane we can represent it as, generally there is a 0 at 1, so it is, this is how we represent it in the s plane, and there are two poles, one at -1 and the other one at -2. So this is the standard notation. Poles are represented like this and zeros by this. And this plot is called the pole zero plot. Okay. And this is very important. The pole zero plot is very important in the study of Laplace transform. Okay. Pole zero plot. So in this particular case, this is the pole zero plot. Okay. Now just one question. In this case, what is the ROC? ROC is real part of S greater than -1. Can this pole be in the ROC? Can it be in the ROC?
No, sir.
No. Because poles are by definition, pole is the value, the root of the denominator polynomial, isn't it? Where the value of that function is infinite. So that integral, that Laplace transform integral, that won't converge there. So can we say that there will not be any pole inside the ROC? Can we say that? By definition, pole is this one, right? If you put any value of this here, it is infinite. And what is region of convergence? The value, the values of s for which x of s is finite. That is called the region of convergence. Since it is infinite, these points are this will never be inside the ROC poles. You can see it here. That is not in the ROC. Here the ROC is real part of s greater than -1. Now what about a 0? Is it in the ROC? In this case, is it in the ROC? What is the ROC here? In this example, it is real part of s greater than -1. In this case, 0 is inside the ROC. But it is not necessary that 0 is, I will give you an example. 3 e to the power minus 2t ut minus 2 e to the power minus 3t ut. Yes. What is the Laplace transform of this? I can write the standard result here. E to the power minus at ut, that is 1 upon s plus a, and the ROC is real part of s greater than minus a. So what is the Laplace transform of the first part of this? Is it 3 by s plus 2? Is it 3 by s plus 2?
Yes, sir.
So this is 3 by s plus 2, and this one is minus 2 by s plus 3. Can we simplify this? And what is the ROC? ROC of this is real part of s greater than -2, and this is real part of s greater than -3, isn't it? So what is the ROC? This is x of s. What is the ROC of x of s?
Greater than minus.
-2.
It is real part of s greater than -2. The ROC means this expression is valid only in this region. This expression x of s is 3 by s plus 2 minus 2 by s plus 3. That expression is valid only for these values of s. Now, can we write it in the pole 0 form? Ratio of two polynomials? What is that? X of s is what?
S plus 5.
S plus 5 by?
S plus 2, S plus 3.
Okay, this is the polynomial form, means rational form of that x of s. And then what is the pole 0 plot? This is the s-plane. There is a 0 at -5, and there is a pole at -3 and another pole at -2. And what is the ROC? Is it this? Real part of s greater than -1? Sorry, -2.
Yes, sir.
So in this case, the 0 is in ROC or not? This is the ROC. Then how this can be in the ROC? This is not in the ROC. So the point is that 0 may or may not be in the ROC, but pole is always outside ROC. It cannot be inside the ROC. But 0 may or may not be in the ROC. Okay, that's why I have shown this example to clarify that. So, any question regarding this? Even though x of let's say zi, that is 0. That would be if you put, when you express it as a ratio of two polynomials, if you put this s as -5, you will get a finite value of x of s. But the problem is that this expression is valid only in this region. Okay? So it won't make any sense if you put this value and here, then saying that it is finite. This expression is valid only in this region, only in the region of convergence. Okay? So this here, this 0 is not inside the ROC, but it can be, sometimes it can be inside the ROC. But pole will never be inside the ROC. Okay? Any question?
So we should include s is equal to -5 in ROC also.
No, that's what
Only
I am
that.
saying. That is what I am saying. What is ROC? The values of s for which this expression is valid. Is it?
Yes, sir.
Then how can you take this function here? This expression is valid only in this region. And this is a 0, it's okay. 0 means it is a root of the numerator polynomial. It can be here also. Okay, if you consider only this polynomial, it has a root here. That is the only meaning of 0. Consider the numerator polynomial, it has a root here. But whether it is in the ROC or not, that depends on whether this point is inside the ROC. That means this expression is valid or not. In this case, this expression, it is valid only in this region. So this point is not inside the ROC. Is it clear?
Okay, got that. Yes.